Well, good morning. I have to give you a little bit of a heads up. I don't do a lot of this, and when Rich first asked me if I would do it, I thought, yeah, it's a good fit, except I'm not a riparian guy, I'm not a hydrologist, I'm not a biologist, I'm not a forester. So what we're really going to deal with today is just the data and my experience with it and what I think some of the applications that you might be able to use it for. I haven't done any of this modeling or... Anyway, I put a couple of slides together and I thought I'd better talk to my wife about it because she's pretty good at this and she likes to do this kind of stuff. So I showed her what I had and she said, okay, how long do you have? I said 30 minutes. And she said, well, that's not going to work. She said, I only have 2 slides. What I do with the riparian stuff, and it's pretty simple. So I said, okay, so I went back to the drawing table and I started pulling in a few slides from here and there. And so the warning is I got it pared down to about 165. So we're going to have to just sort of go through these. Some of them I'm going to skip through. Lots of images, and I think we'll just try and have some general discussion about what we're looking at, and again, how they could apply to what you're going to use them for, what you could use them for. So a little bit of an introduction. So about 4 years ago, I did a fairly major FRIA project with Sundry Forest Products. And just a note on that project, we committed together to a couple of things that were fairly important in terms of the tack that we took for the project. One was that we would try and produce some very simple deliverables that anybody could take to the desktop. Another was that we would try and look at the potential for modeling complex structure. To that point, it seemed like most people were working with just trying to identify simple structure. Then 2 years ago, and the other was that we would try and develop some tools for quantifying structure. And then about 2 years ago, I did a project with Shell Canada. In the Fort McMurray area, they wanted to see if we could use LiDAR to quantify low veg as part of a process in the getting reclamation certificates for the access and what they call OSE sites. So we were trying to quantify the low veg on those in terms of are they ready for reclamation certification or not. And when we did that project, we realized that some of the things that we'd done with Sundry Forest Products weren't going to work because of the resolution. The access roads are very small, much like riparian boundaries in some cases. So we had to rethink some of the things that we were doing, and that's kind of what we're going to bring to the table today. I want to spend a minute just talking about this data information knowledge paradigm because I think it is very important. It comes really from a guy that I had a class from when I went back to school, a great guy who was from Ohio, a visiting professor, and it was a LiDAR course. And he spent a lot of time on this, and I thought when he was doing it, I thought, man, I wish he wouldn't spend so much time on this. But ever since, I've really, remembered what he emphasized. And one of the primary things was that we should never underestimate our abilities to do scene interpretation, and that we'll never train a computer to do all of the things that we can do. So we really need to understand this sort of paradigm. There's tons and tons of sensors out there now. In fact, there's 2 U.S. satellites. They collect 2 terabytes a day. Collect and process 2 terabytes a day. And they archive it in silos, like literally silos now. Lots and lots of raw data out there. The raw data itself doesn't have a lot of value. It needs to be processed. LiDAR is a little bit unique in that it's vector data. It's delivered as vector data. When we think about remote sensing, we think about images. That's just what always comes to mind. LiDAR is actually vector data, so something has to happen to it. There's ground data and above data. That's the way it's delivered, and we have a pretty well-defined set of deliverables for the ground data. I'm not going to speak to them at all. I think everybody is probably familiar, utilizes them. They're fairly commonplace. What's new is trying to find ways to utilize the above-ground data. Until very recently, I think a lot of clients, LiDAR clients, didn't even want the above-ground data. They said, just deliver us the DEM stuff, that's all we want. Now, people are trying to find ways to utilize all of this information that's above the ground. So, in this example, there's information that's implicit in the data. We need to find ways to make it explicit, and so we need to transform it. Again, the LiDAR is vector data, so we're trying to transform it into some forms of raster data where we can explicitly extract the information to gain knowledge. The examples I gave, the one on the left is a DEM. So the DEM, as we saw in the previous slide, it has actual elevation values. The data is still there, it's still intact, but it has no value in terms of scene interpretation. We would never bring RTM to look at it and try and understand what's going on in it. The next image is a slope class image. So it's slopes that have been put into classes and then colored according to class. The actual values are still in that image. They are actual slope class values. They can be quantified, they're still completely useful, but we have an image that we can now interpret. And the next one, the hillshade, which everybody knows and loves, it's got that huge wow factor. It has no information in it. It's gone. It's now just pixel values that are nothing but colors. So we can't use the actual data from that image for anything. But it's a wonderful tool for scene interpretation. A note on the hillshade, I always recommend people use that in conjunction with some other data set. It's based strictly on the sun angle and the information that the user inputs to generate it. And like good advertising people, you can manipulate that. If you change that, your perceptions from the image will change, or they can change. So if you use it in conjunction with contrast or the slope class, something that can give it more context, you won't have those issues. And the knowledge then, it's again not as well defined, but it's, you know, this notion we hear all the time. Now I know what to do. When you understand something, you gain knowledge. And decision makers, I mean, you're all decision makers at a very high level. You make decisions based on information. So you're trying to get the most knowledge, or you're trying to get the information out to understand things to base your decisions on. So what we're going to look at primarily is, okay, so what can we do with this LiDAR to try and transform it so that it has information that we can turn into knowledge in our decision-making processes. Okay, understanding your data. I know everybody knows already that's a very, very important one. We can't ever predict all of the things that we're going to find in the data or not find in the data. There's sometimes, you know, things that just don't work. I don't know how many times this has happened to me. It probably happened to you guys too. You know, you go through something, wow, this is great, this is really working well, and then all of a sudden it falls flat. You miss something. Something else is, you know, come up that's not there. So I want to spend a little bit of time just looking at the data. It's the deliverables. Oh, this is I'm just gonna. We could back up and go through that. No, we won't go through
I could put
these.
back.
That's okay. These are the deliverables. For those of you who don't know, again, here's the DEM, but this displayed as a hillshade. We get an intensity, full feature, shaded relief, and the point cloud. And the point cloud is the one that we're going to focus on. The other ones that they processed, and typically the hillshade is the one that's primarily used. The others have some value, but it's not extensive. This is the one that's really important, is the point data set. This is a typical tile delivered from the Government of Alberta data set. It's about 2 kilometers square, and it has about 11,800,000 points in it. Anybody ever tried to bring up 11 million points in ArcGIS or any other piece of software? Doesn't work well. So what are we going to do with it? The points are discrete. Every one is a discrete location. The only information is the exact coordinates of the point, the X, Y, Z. That's how it's recorded, and that's how it's delivered. I put this image in. It's just a strip from that very tile. It's a 2-meter wide strip. Shows it's got 3,800 points in it. And down below, it's not that visible, but you can see it's a canopy image. The tops are colored. The tops of the trees are colored, and the rest are not colored. But you can distinguish that they're trees. The reason I put it in is I want you to notice that it's forest on the prairie. Anybody ever been in a forest that ground as flat as that? It doesn't grow there, does it? The first thing that needs to happen with this data is you have to transform it so that it has a height above ground instead of an elevation. Okay, if we displayed it in its actual form, it might be up and over a hill and down. When you looked at that image, you would still see the trees, but you couldn't interpret the same way. If you're wondering what the relationships are, you'd have to piece through the image. When you transform it so that it's height above ground, now we can strike a line and we have information about the entire image that we're looking at. So this is the first transition, and a very important one, with the point data. This image is a point count, and I've always thought this was the very, very most important image to be delivered with a data set. It's a great image for doing QC on the acquisition. It's also very important in helping to understand if you're modeling what your data is like. So for example, if you were modeling, this is an area of interest, it's got 25 of these tiles in it, so it's about 50 kilometers square. And if you had some field plots, and they fell in this strip here, say you had one up here, the data looks like this. If it's here, the density is much, much higher. Then it gets low again. We've got gaps here, we've got gaps here. Down here we've got lots of other stuff going on. The density of the data is very inconsistent in this image, and I put it in because it's very unusual. You'll probably never find another one like this. This is sort of the conjunction of 4 projects. They might be from different years. If we look at it, you can actually tell the direction of flight here would be in this direction. You can see the overlaps have more higher density. In this one, you can see the flight direction is here. We've got some gaps in the overlap. We've got a lot of rough weather going on. Here's the plane pitching and going all over the place. This one is flowing east-west, and again, some gaps going on here. This one is also east-west. 4 distinct projects is what I want you to recognize. The reason that the density is so high in these dark green places is that we have point data from all of those projects left in. Nothing wrong with that. They should all fit. Everything should be fine. But you can see some very, very sharp seams. Like here, where they've taken out the data. Below it, they haven't. Again, here, they've taken it out. You want to be able to look at this, because if you're trying to build a model, everybody, I think the consensus would be this government data is not suitable for individual tree modeling. It just doesn't have the density. You say, oh, I get great results. Like, we're doing individual tree modeling, it's working perfectly. And then you realize that you're doing it in this area. Okay, that's why it's working perfectly. You have very high densities there. If you try and apply that outside of that area, it's going to fall apart. This is the same area, same data. It has no elevation data in it whatsoever. If you look at the scale, I masked out what the image is based on. I thought you might think about it a little bit as you look at it. The values are from 0 to 100. So it would tell you this image is probably a proportion image. Okay, it's looking at a percentage. But what is it? Well, the first thing to think about, and again, this is scene interpretation. This is our ability to look at it and try and understand it in a way that we'll never get the computer to do it. If we look at it, we can see certain features. We see lineal features. We see anthropogenic features. It looks like we see topography. This is not draped on a DEM. There's no elevation data in this image whatsoever. This is probably the first image that I ever saw. Maybe it's the first one that you saw that tells us there's a direct correlation between vegetation and topography. What we're seeing is varying vegetation. The topography that we're seeing, the variation comes from, what would the attributes of the topography be? Anybody want to hazard a guess? That's affecting the image. Slope and aspect. Okay, these southwest facing slopes or west facing slopes, they're quite dark. They have low proportions. This is the proportion of data that got to the ground. So this is a ground image, a ground proportion image. It's very dark, no data got to the ground. Very bright, all the data got to the ground. Okay, and when you look at it, that makes sense. You can see in the top part, there's probably no vegetation. It doesn't look like it's disturbed, but it looks like there's no vegetation. The rest shows vegetation, but varying with aspect and topography. So the LiDAR can help us identify the fact that vegetation will vary with aspect and slope. We don't know which part of the data set yet. Is this way up high in the data set, top of the canopy, or is this close to the ground? We don't know. We just know that it will vary with topography, and everybody here probably intuitively knows that from your experience. I put in a couple of slides that just show some anomalies from the bottom corner, and when I discussed them, I just wanted to point them out. What you see there, those do relate to acquisition. If you see this in an image, it relates to acquisition. You need to go back to the guy that flew this or get somebody to have a look at it for you. It doesn't relate to anything on the ground. That's just a blow-up of it that shows the changes in density and where that's located. Another one here. But I'm not going to discuss those again. In the bottom corner, you can see the only place, it's only from that one project. Whatever project it was that was flown in that bottom part. Maybe it's a different sensor, maybe a different elevation. Something is different going on there, but you need to explore that with your provider. This image is just from 0 to 2 meters above ground. So this is how much data was captured above the ground, but below 2 meters. And again, the brightnesses depict the proportions. If we look at the next image, we'll see that really it's the inverse of the ground data. So this area is the best example. It shows very low proportions of ground data here, very high proportions of low veg. Okay, and if we look at the aspect in the slope, that probably makes sense to you. Okay, that aspect, you could probably even tell me what the vegetation is. But a direct correlation between these two images, this helps us to understand that the aspect and slope influence low veg. Okay, this is the veg that's within 2 meters of the ground. We don't know about the other vegetation yet. This is a canopy model. This is right from the top. So these are the heights right at the top of the canopy. We don't see any issues with the acquisition. All of those have disappeared. We don't see any topographic features. We see some disturbed features. We see differences in heights, but we don't see that same sense of topography. So that aspect slope relates to low veg, not high veg so much. Make sense? Okay, the other thing you need to be aware of, the point data, again, we're trying to find ways to transform this into image data, into raster data or grid data. Okay, the one at the top is at a 0.5 meter resolution. You can see very clearly some problems here. Okay, there's a line here and these stripes. Is that something that relates to the ground, to the actual physical nature of the topography? It's an acquisition thing, absolutely, no question about it. The fact that it's such a straight line would indicate it's probably one of those tiles where they cut out the data below it. Okay, it's a very straight seam. If it related to a gas acquisition, it'd be because the aircraft was bouncing around. It wouldn't be a straight line. It would be all over the place. The bottom one is at a higher resolution, 5 meters. It's disappeared. Okay, again because we're masking over all of those areas where there is no data by enlarging the pixel size. So one of the questions you have to ask yourself is, if you want to model at the landscape level, what's an appropriate resolution for the data? Okay, at 0.5 meters, if I'm building models, I'm going to have some problems with that issue we're seeing in the top image. If I go to a larger pixel size, I'm going to mask over some of that, but I'm going to lose some information. I'm not going to have the detail that I have in the other image. So you have to ask yourself the questions about that and then try and balance that, what's going to work and why. So the common strategy for trying to quantify, these would be grid cells. It's just a fixed size. I think these were at 15 meters. The idea is you subset the points again as they have to the tiles. They didn't deliver the LiDAR as it was flowing. They subset it down to these 2 kilometer blocks because of the file sizes and the amount of data. The idea here is you do the same thing. This would be the common strategy for, I think, most people who are using it to model. We're turning 462 points in the example into 100 in a polygon, or in a point. It doesn't matter. It can be in a, but it's going into a vector format, and it can have many attributes. So typically, people generate metrics that relate to the distribution of those points within that area. And then those metrics are used to try and model attributes. Okay, this is a typical strategy of trying to divide and conquer. Again, after you've done the dividing and conquering, you've got to find ways to piece it back together because you're interested in more than a 15-meter area. But this is the most common strategy, and what we're going to look at an alternative for here today. Here's an example again of the cells laid over. This is a canopy height model on top of the ortho. That's a field plot. Again, the idea is the notion is very common now. You calibrate it. You need to collect some field data to validate what you're trying to model with your LiDAR data. So this is a field plot. Again, one of the issues, this is a fixed radius plot. They're not square. They're round. The grid cell is square. That's the reality of it. So you have to look at the impact of that. Locating the plot is very important. You have to make sure you're looking at the right data and so on. I put this one into just help you understand the complexity of that. It's a really, really tedious thing to do. If your plot is slightly off and you're using different LiDAR points, what's the effect going to be? So you have to have a strategy for trying to determine the accuracy of your plot location and whether you're using the right LiDAR points to build your models. So it's quite a rigorous exercise. Then, once you have the metrics built into your tiles, as you see here, you take those metrics into a larger polygon and use them to model attributes for your larger polygon. So this is the common strategy. The drawbacks, the grid cells are like a pixel size. So commonly used are 15 meters. Some people in this area have used 18 meters, 20 meters, 30 meters. I'm sure everybody has seen these images at a landscape level, but that's your pixel size. You can't model anything smaller than that, as with any other image. Okay, you'll have many attributes in each one of those squares. You can create many images, but you can only create it at that resolution. This image, this is the 0.5 meter canopy height model with some polygons that were automatically generated. The idea that we had when we did the shell project was, well, we can't use those grid cells. These axes are only 5 meters wide. We can't use a 15 meter pixel to model 5 meters. So we said, well, why don't we just look at the images themselves? So we looked at the 0.5 meter image, which is the highest resolution that we produce, and said, why not just summarize the pixels? Okay, I'm using the word image consistently, but in fact they're not images, they're grids. Okay, the actual values are still in the images. Okay, we embed a color map so they always come up with color, and that will change depending on the client or their preferences. But they do have actual values. So all we did was take the actual values of the pixels and create a distribution of them in the polygon. Okay, this is just an example, again, of some polygons that were generated. It doesn't matter how many you have. They can be contiguous or non-contiguous, and you just pull the values within the polygon and summarize the heights. So these are height class distributions within the two polygons. The yellow indicates where Rich had some plots in the that we did with Rich. Okay, from those distributions, those variables, that's what we would take. That's what you would take. Here's your independent variables. You're going to transform those into hectares. I have this many hectares at this height, and use those to model, whatever attributes. You could transform these in a number of ways, but these are the basic variables that you're going to input into your models to build some kind of an algorithm. So that's the approach we use with the shell project, again, because we're modeling low veg in very tight polygons. A couple of other examples, again, of the distributions, and you can see the pattern. There's a very distinct pattern with them. There's relationships there. It's defining them. The larger the pixel, the bigger the problem. Here's an example of 15 meter cells in two polygons, two different attributes. So the first one uses the 94th percentile height, and the second uses the modeled height. And again, you can see how they correlate or how they don't correlate to those polygons that came from the original LiDAR image. And this, again, that's the common methodology. Same polygons with a max from a larger size pixel and from a 5 meter pixel. So a 5 meter and 15 meter pixel in this example. And you can see what gets masked over as the pixel increases. Okay, all of a sudden we think we died and went to forest heaven. Well, we're just maybe looking at one tree in a 15 meter area, but the pixel is colored according to that tree. We don't know anything else about it. And when we get to that resolution, we don't know anything else about it. Here's an example, again, of the same polygon and 3 different ways to summarize it, or 3 different resolutions. So the top one is at a 0.5 meter resolution. Again, the thing that stands out, what do we gain at this resolution? We see the densities. Okay, we know how much is open. As the pixel size increases, we start to lose that. And the larger the pixel, the less we know about the densities or the canopy closure in it. We get a good sense of the heights, some other attributes, but not the densities.
Just before you go on,
yeah.
Did you do any ground truthing on those height distributions?
None of this has been ground truth. These are just the I'm going to give you.
Okay.
But I do have a little bit of statistics that will come from Rich's, the little project we did with Rich.
Okay.
Another example here, same polygon. Now, the other thing that we did with in the shell project, and again in the FRIA project we did with Sundry, we created, these are 2 rasters that we created with them. Again, because we were committed to trying to look at complex structure, or can we understand multi-story, we looked at low vegetation. The bottom image is based on data within 3 meters of the ground only. The top image is based on the whole canopy. The top image is in 1 meter increments. It has a 1 meter vertical resolution. The bottom image has a 10 centimeter, a decimeter resolution. So the purpose of this was, again, to see, can we identify low vegetation with a LiDAR? Or can we only get the overstory, can we only do single structure? So this is the approach we used with the shell stuff, because it was all low veg. It was all 20 centimeters, 30 centimeters, 40 centimeters, no more than that. If we did it at a 1 meter resolution, we wouldn't have anything. Broke it to a 10 meter resolution and produced the same image down low. And there's the distributions. I put 2 of these slides in because it's a very important point. The one thing that's missing in the deliverable from GeoA is height of ground. We don't have it. You have to get that in. The strategy that the GeoA government uses deliverables would be, you take the full feature, all the points, the bare earth, you subtract them, you get the height above ground, which is absolutely correct, and it's very commonly done. The image below comes from that. Okay, you have a grid, you have 2 grids, they both have error, it's at a 1 meter resolution. When you subtract them, there's what you get, and there's the distributions. The image above, the heights above grounds were calculated for the points, and then the image was built from the points. It's quite different, and the bottom methodology does not work well with this in this particular process. Okay, one more example here, and I'm running out of time, so we're going to hustle through here. 2 images, other applications, and then we'll go right to the riparian stuff. Linear disturbance is another very important thing and very popular topic at this point. The seismic line that's visible here, it may not even be a seismic line, might be a hand cut. You can pick these up quite easily in the LiDAR. You don't always get them in an ortho. If you looked at the understory image I just talked about, here's what you see. So right away you can tell where this line is. You can also tell it's vegetated. You could put a polygon on that and quantify how much vegetation. So this is another application for the same data sets. Just some more examples of a distribution. These are just typical polygons. Here's the bottom one would be a typical inventory polygon that would be termed or looked at as riparian. The riparian ones, here's a couple of examples for riparian. This is a simple buffer, like Rich talked about, 10 meter buffer. There's the overstory distributions, and there's the understory distributions. Again, those are the variables that we'd use to try and model or quantify other structures. This one comes from Barry's mapping. These are polygons that came from wet area mapping as opposed to a fixed width buffer. And there's the results. Same thing, you can just populate from the image itself. And then I generated one that I think this has the most potential. This came from normalizing the DEM to the hydrology, so to speak. So we took the channels, that now becomes ground zero. Just like we transformed the elevation of points above ground to heights above ground, this polygon is based 2 meters above stream channel. So 2 vertical meters above stream channel, it forms a polygon. These are the polygons that came from a little area that is again in Rich's project. And again, you could summarize them, break them up, summarize them how you choose. A couple of examples of the structure and the summaries and the understory. This is the fixed buffer for the little project that, or one of the areas in Rich's little project. Again, he had plots within these. That's what the numbers are. This would be the understory, and in this project we just generated a coverage of polygons and then clicked his buffer and populated those. And wherever the plot fell, that's the polygon that he modeled with. And these are the results that came from Rich's project. Again, he kind of displays the field data as opposed to the LiDAR data, and the statistics that he got for the 3 variables that he was looking for within those polygons where he had plots. And then a couple of just slides on polygons. How can you generate polygons? These are automatically generated from the LiDAR. This is targeting low veg. This is targeting low veg non-merge. This is targeting a certain height class. And that's it.